Today we're learning how to solve for one measurement of a gas when three others are given and when nothing is changing. This is called the ideal gas law. So we already had the combined gas law that had the ones and the twos for when things were changing. Now we have the ideal gas law for unchanging conditions, when you just have one pressure, not two, just one volume, not two, just one temperature, not two, just one moles, not two. You have just one pressure, volume, temperature, or moles, and you solve for one missing thing. The math equation is PV equals nRT. P is pressure, V is volume, N is moles, T is temperature, R is new. R is called the ideal gas constant, and you need to memorize its value because it is not on the back of the periodic table. The equation is on the back of your periodic table, so you don't need to memorize that, but the value of R is not, so please memorize it's 0.0821, and its units are pretty important because they determine the units that the rest of the problem needs to be in. So the units of R, I told students, is what you drink on your cereal in the morning, what you put on your cereal in the morning, which is animal milk, atom, ol, molk. So atmospheres, liters, moles, Kelvin are the units of R. So because R has those units, you must always use atmospheres, liters, moles, and Kelvin when you use the ideal gas law. If you don't, your units won't cancel out. You're basically using the wrong constant, and you'll get the wrong answer. So in the combined gas law, with changing conditions with the ones and twos, use whatever you want as long as you convert to Kelvin. With this one, you have to use atmospheres, liters, moles, and Kelvin. For example, a can contains 0.01 moles of steam at 25 degrees Celsius and 765 millimeters of mercury. What is the volume? So in this problem, we have a moles and a temperature, a pressure. We're asked for a volume. Notice there aren't any first and second moles, no first and second temperatures, no first and second pressures, no first and second volumes. Just one set of conditions. So we have our N, that's the moles, 0.01 moles. Our T, that's the temperature, 25 degrees Celsius, but we will need to make sure and use that in Kelvin. Our 765 millimeters of mercury is our pressure, but we'll need to make sure and use that in atmospheres. And we're trying to solve for our volume. So once you identify that problem only has one of each gas measurement, you know that the equation is the ideal gas law. PV equals nRT. We're trying to solve for V, so I'm going to divide by everything that is with the V, which is the P. So the p's cancel out on the left side, and my equation is V equals nRT over P. Now I plug in my numbers I'm being very careful to use moles and atmospheres and Kelvin and liters. So my N is 0.01 moles. My R that I need to memorize, 0.0821 atmosphere liters over moles Kelvin. Please write the units so you can remind yourself to use those units in the other numbers. My temperature is 25 degrees Celsius. You have to convert it to Kelvin, so we're going to add 273. And my pressure is 765 millimeters of mercury. I need to use atmospheres, so I will convert my units. I find the numbers that go with the pressure units on the back of the periodic table. Millimeters of mercury is 760, and atmospheres is 1. So then I plug this all into my calculator. Well, actually, first I should check and make sure my units cancel out. So moles cancel out, Kelvins cancel out, atmospheres cancel out, millimeters of mercury cancel out. So yes, all I'm left with is liters, which is the unit of volume I'm expecting when I use the ideal gas law. So that's all good. Now I plug this into my calculator. Make sure and use parentheses if you're doing it all in one step like this on the bottom. And you should wind up with 0.2431 liters.